Okay, question 3. It's a beast basically. It's easy but it's hard at the same time. First thing here is, this is I think the easy bit really. When you get given a number like this, 3.5 times 10 to the 3, why do we use standard form? Well, it makes things easier to estimate relative sizes, but also it allows us to show uncertainty. So because this is a 2 sig fig number, the last digit implies the uncertainties. This is really saying well, it's 3.5 plus or minus 0.1 times 10 to the 3, obviously. So so here we basically say, well, this is the uncertainty, the 0.1 over 3.5. Multiply it by 100 to get a percentage, and of course that comes to 2.9. You could have said 3%. That's fine, but 2.9 to 2 sig figs. If it said something like 3.50 times 10 to the minus 3, well, of course the uncertainty there would have been 0.01 divided by 3.5. So this idea of standard form, this notion here is really key to expressing uncertainties in number. We then of course have to determine the grating spacing. Now you look down here and you're thinking, oh, it's in millimetres. So you've got a choice. You can do it in metres and then convert, or you could just do it in millimetres from the start. I chose to do it in millimetres. There are 1,000 millimetres in a metre divided by the number of lines per grating per metre. So there we go, 1,000 divided by that gives you 0.29. Now this next bit, state the absolute uncertainty value. This is really key, the word here, state. It basically means you don't have to do a calculation. So this is a value. We've got this uncertainty 2.2 sig figs. We've got a raw value there to 2 sig figs. We've got a grating spacing to 2 sig figs. We're just going to state the uncertainty. Now this is 2 sig figs. It's 0.29. Of course, because it's 2 sig figs there, the last one is the uncertainty. So it's basically 0.01. Oh, sorry, yeah, 0.0, I was just drawing in 0.01. So it implies that is the absolute uncertainty. You could do it by taking the percentage uncertainty and that, multiplying by the grating spacing, and you get a value that rounds up to 0.1. But when it says state, you don't need to. Okay, so that's 0.01 there. This one here, disappointed with the number of people that didn't recognise when you see the opportunity to repeat readings, you take it. So it wants to work out the distance between two adjacent maxima in the interference. And you're not going to go, I'm going to measure from that one to that one. Of course not. You're going to measure between a whole bunch of them and divide. So this value here is 0.6 centimetres or 6 millimetres. This value up here is 13.6 millimetres. So the difference between them, of course, is 136 millimetres minus the 6 millimetres there. And then you count out, you don't count the first one, we're counting the spaces. So leave that as 0, I suppose. And you're going to say 1, 2, 3. When you count up to there, you realise it's 25. So that's how we set it up. That's the separation of 25. That's the length, I suppose, of 25 maxima divided by the number of maxima gives us 5.2 millimetres between each one. And a lot of people read that as being 0.6, which is a huge error really. 2.5 versus 0.6. Sorry, 2.5 versus 6 millimetres, a big error. So that's that one, fairly straightforward. This one is a beast, and I have to apologise. It's only 2 marks, but it's a real evil question. So calculate the number of lines per metre on the grating. It really should be worth more marks, but it's the same for everyone. So here's how it works. First of all, we know our famous equation, the Bagg equation, n lambda equals d sine beta. So we kind of got to basically, we know the spacing of the maximum is 2.5. We've got to try and find something to do with this. So the first thing we're going to do is work out what theta is. We know the individual patterns, okay, here are 5.2 millimetres apart, and we know that it's 2.5 metres from the laser, from the diffraction rate to the swing. So you think about for the first order, let's suppose this was the central one there or something, we're thinking about this first order here, it would be 2.5 millimetres at a distance of 2,500. So to calculate this angle in here, we're going to do the inverse tan of the opposite over the adjacent. That gives this tiny angle, 0.045896, whatever. That's the angle. Then we're going to try and plug this into n lambda equals d sine theta. So sticking with the first order, when it's 5.2, we can get rid of the n, it's just 1. Rearrange this to make d the subject, therefore we get d equals n lambda over sine theta. Again, like I said, just drop the 1, drop the n there. So lambda is 680 nanometers, so I'm timesing it by 10 to the minus 9, divided by the sine of this angle I've just calculated there. That gives us a grating spacing between each line of the grating of 8.5 times 10 to the minus 4. Now finally, if we know the spacing between individual lines on the grating, we can work out the number of lines on the grating. So of course the number of lines will be 1 meter divided by the spacing between each line, and that, when you do that, 1 divided by that, you get 1176 or 1,200 lines per meter. A beast of a question, but anyway, only 2 marks for that. Stay and explain. Once you've done this, obviously it's clearly not, but of course that word there, explain. So we know that the lines that it says on the packet up here has a mark 3.5 times 10 to the 3. We've calculated the percentage of uncertainty as 2.9, so we're basically saying that this value falls outside of the range that is given by the 3% error, the 2.9% error. Again, it really doesn't matter, you can get error carried through as long as you are saying what you found either does or does not lie within the range. And it's this word here that seems to be getting people when it says explain. People just are dropping it. Finally, safety precautions. Well, there's loads. You can't wear eye protection against lasers. A lot of people are saying wear eye protection. It doesn't work like that. If you have a protection that stops you getting hurt by a laser, then basically you can't see what you're doing. You may as well, just, it won't work. So that's the silly thing to write. Instead, we want to say that we're going to have no reflective surfaces so it can go in our eyes. We're going to operate in the plane of the table, keeping your head above it, or words to that effect.